So I want to talk now about another force. And this is the force due to a spring. So what's a spring? Well, we're thinking like a slinky, right? Or a coil of metal. Although this generalizes to a larger class of things. So how do you draw a spring? Perfect. Okay, so let's put a mass on that guy. So there's some mass. When you stretch this spring, what happens? Well, I'm going to stretch it maybe some distance away from this location. And this location, we're going to call that the equilibrium position. We'll say equilibrium. Meaning that's where the spring wants to rest, right? That's where there is no force due to the spring. But if I stretch the spring a little bit, so a stretched spring is like this. And there's my mass. So I've now stretched this spring by some delta x. And the spring acts to the spring acts to apply force this way, right? That's my spring force. All right. And if instead I compressed the spring by some distance, so this is my new delta x. The spring force would act again against the delta x. So that spring force is a restoring force. The spring force is a restoring force, right? It wants to put the system back in equilibrium. Okay. And in fact, for many materials, you could plot the spring force versus position, or really displacement from equilibrium, and you would notice that when you pull harder from equilibrium, the restoring force gets bigger. Also, they are opposite directions, right? So when delta x is positive, so in, say, this region, the spring force is negative, so that's here, right? So this exists in these two quadrants. Let's just sketch it. Sketch it in red. I'm sure I can do better. I mean, for that to pass through 0, 0. Okay, so that's a straight line. Well, mostly a straight line. And the equation of this is Fs equals some negative constant times delta x, right? And in fact, that's a vector equation because the force is a vector and the delta x is a vector. And that negative sign then indicates that they point in opposite directions, which they indeed do. So this relationship, spring force equals minus k delta x, is sometimes referred to as Hooke's law. And Hooke's law is true for lots of systems, particularly lots of systems with small displacements. We see that if you displace an atom in a crystal a small distance from where it wants to be from its equilibrium position, there is a restoring force because it was where it wanted to be. So if you move it away, it's going to try to go back. And that's roughly linear until you move it really far. And in fact, if you've ever given a child a slinky, you'll notice that if it gets stretched past its elastic limit, it'll deform and it'll stop being a perfect spring, and it'll have a bunch of kinks in it. So I'm going to suggest this. Hooke's law is not really a physical law in the same way that Newton's second law is, right? You cannot break Newton's second law. Newton's second law is always true. Hooke's law is only sometimes true. It's a useful thing, but I'm going to call it Hooke's good idea. Because again, it's not a physical law. It's just a useful observation. Okay. Let's talk about this K. K is the spring constant. And I just wrote sprung constant. There. K is the spring constant, and it must have units of newtons per meter. All right, and that's a kind of a measure of how stiff the spring is, right? A very small spring constant would be for a spring that supplies a small force for a displacement. This would be like the spring inside of a pen, right? Some pens have a push button, right, to extend, and that spring has a very small spring constant because you only need a small force. Even if the displacement is small, you only need a small force. Versus the spring in, say, a shock absorber in a car, right? That spring, or four of those springs, support the weight of the vehicle. And so they have to have a much higher spring constant. Even if they're only displacing a small amount, they're supporting a much bigger weight. So let's do an example. I'm going to go back to the Chapter 5 handout and look at example 7. So this is a pretty simple example here. A 12 kilogram mass is hung from a certain spring. The spring stretches 7 centimeters. How much mass would be required to stretch it 15 centimeters? Okay, so we could draw this picture. But let's draw it not with yellow as the ceiling. So there's our ceiling. And that's, say, our unstretched spring. So this situation is different than how I drew this when I introduced it. Now this spring is hanging. So the spring should be experiencing gravitational force. So it ought to stretch a little bit just under its own weight, right? If you think about this part of the spring is supporting this part of the spring. So I could say the top half is should be stretched by the bottom half of the spring, and you could do that for any combination of the top third and the bottom 2/3 or something like that. So often what we do is we treat an ideal spring as massless, so that it does not stretch under the force of gravity, so that it only stretches when I add a mass to it, right? So if I add a mass, it stretches some distance. This could be our mass 1. Right, and it's stretched. Nope. So our displacement here is maybe that far. Delta x. I could call that delta y. It doesn't really matter. I'm going to leave it as an x for now. And there's my spring force acting upward. And do you see the spring force here is acting against weight 1. And in this case, we're in equilibrium, right? So the object is at rest, right? It is stretched as far as it's going to stretch under this weight, and so I can see that the spring force equals weight 1. All right, and the question is, if I put this under another mass, in fact, the second mass we don't know, but we know the second distance is 15 centimeters. So if it is stretched further, call this delta x1, This could be delta x2. And I guess this would be spring force 1 and spring force 2. The question is, what is the mass? What is M2 that causes spring force 2? So clearly it's going to have to be bigger than 12 kilograms, and in fact you might be able to figure out a ratio way of solving this, but I'm going to solve it in a different way. I'm going to say, let's first solve the spring constant, so we'll say find K, and then step 2 will be find M2. I can do better than that. So we'll do step 1 first. Right, so we're just saying the spring force equals weight 1. Right, and spring force, remember, is minus K delta X. But I don't really mean, well, I guess I could say delta X is down, so delta X is negative, so those two negatives go away. But I feel like it's more useful here to say the size of the spring force equals the size of weight 1. So I often do not include this negative sign in the math. I know that the negative sign means the spring force is the opposite direction of the displacement, and I've already taken that into account by drawing this arrow up. Right? So I usually don't even worry about the negative sign, and I just know that I'm using magnitudes. So K delta x1 equals m1g. Okay, this lets me solve for K. Let's do one more line here. K equals m1g over delta x1. M1 is 12 kilograms. G is 9.8 meters per second squared. And that delta x is 0.07 meters. So I get a spring constant here that is 1,680 newtons per meter. Notice that I could have left this in centimeters. I could have left it as 7 centimeters downstairs, and I would have gotten 16.8 newtons per centimeter, which is not wrong, it's just not the SI unit. Okay, that's not my answer, though, so maybe I shouldn't put a box around it. Maybe I should just put an underline. Because now I'm going to go up to 2 and say, all right, so FS2 equals weight 2. Right, and FS2 is K delta X2 and equals M2G. Now what I don't know is M2, so I can plug into that, and that's 1680 newtons per meter times 15 centimeters, so it's 0.15. I'm running out of space, so I'm going to move this. I'm going to move this line down a little bit so I have more space. Okay. So, K. Sorry. That's 1680 newtons per meter times 0.15 meters equals M2 times 9.8. If you do that math, you end up with 25.7 kilograms. Fabulous. Okay. So this is actually a pretty simple problem. I tried to go through it pretty explicitly so you could get a sense of the procedure. Let's think about something else, though. Let's think about energy. Right? The spring force is conservative, meaning the work that the spring force does not depend on how you get there. Like, I could stretch the spring here. I could do this stretch first, and it would take me some energy, and then I could go back to this stretch, and I would get some energy back, right? Meaning I have to do work to stretch it to 15 centimeters, and then I get some energy, some work back from the spring force to let it go back to 12 centimeters. If that's the same total work as if I had just stretched it to 12 centimeters initially. All right, that's an indicator that this is a conservative force. So I should be able to define a potential energy. So let's go back and do that. So how do we define potential energies? Well, we looked at the work energy theorem. So let's remember the work energy theorem. That's work equals delta energy. And when we defined gravitational potential, we figured out the work done by gravity and saw that it ended up being a change in some quantity, and we moved it to the other side. I want to do the same thing here. So what's the work done by a spring? What is the work done by a spring? Well, work is force over some distance, and sometimes we say F parallel. But here, the force, the spring force and the displacement of the spring are definitely parallel. Really, they're anti-parallel, so we're going to have to include that negative sign. But also, the force changes as a function of position. The force changes as a function of position. So instead of doing a straight multiplication here, because this would be an area, this would be a straight multiplication, I have to integrate this. Now, I do not expect you to do integrals, but I wanted to talk about it. That you actually have to integrate this force, which is a function of x, over x, from some initial place to some final place. Okay, how does that help us? Well, I wanted to remind you, and I'm not going to you could plug the spring force in here and actually do the integral, but if we just plot this, there's x, and there's the spring force, and if you recall, or if you will trust me, that this quantity is an area of f of s, then we'll actually be able to derive this pretty quickly. So let me just draw a line and maybe give us some limits for this. So let's go from x initial to x final, and what we're looking for is the area of this trapezoid, right? That should be the work done. That's the work done. Okay, so that trapezoid looks like this triangle minus this triangle. And I know how to take the area of a triangle, right? It's half base times height. So we could do that. So the work done here ought to be the area of the big triangle minus the area of the small triangle. So half base times height. Well, the base for each of those, the base for the small one is x initial, the base for the big one is x final, and the heights here should be, let's use another color. The height here, that's f initial, right? And this one is f final. So I could plug those in. I could say half f final x final minus half f initial x initial. And remember, this is following Hooke's law, right? So f equals minus kx. Here I'm leaving off the delta x because this is passing through 0, 0. So delta is a distance from 0, so that's just the straight position. Okay, so I can plug that in. Again, I will never ask you to derive this, but I'd like you to see where it comes from. So this is minus F final. F final is Kx. So it's minus Kx final times x final minus half minus Kx initial times x initial. Okay, why did I include the negative sign? Well, because the area here is negative because it's below the axis. Okay, so we'll do one more step here. Minus half Kx final squared plus half Kx initial squared. And this is the work done, right? And again, we say equals delta E. Now, when we define a potential, we move that term from the work side, this is the work side, we add that or subtract it over to the energy side. So if I subtract that over to the energy side, I have work, let's make this black again, work equals delta E, which is the kinetic energy and whatever else, whatever other potentials we're including. And in this case, we're adding, so it's plus half Kx final squared minus half Kx initial squared. And notice that is just the change in some term that is half Kx squared. So if I define the spring potential as half Kx squared, then I can write this as delta E plus delta U spring. Okay, so if that derivation made no sense, don't worry about it. Just recognize that spring potential, the energy stored in a spring, is half Kx squared. Or sometimes we'll say delta x, depending on where you're calling x equals 0. This is great. This is great because spring potential should not depend on whether you're stretching it or compressing it. Right? You get the same magnitude of force either way, and that x squared takes care of the sign. Whether you're stretching it or compressing it, you're storing some energy, some positive energy either way. Also, look like there's no way to have negative energy for a spring. That's fine. That actually makes a lot of sense. We had negative potential for gravity, and that also made sense because we could fall in a hole and lose. We could always lose more potential, more gravitational potential. But here, there's no way to do that. Okay, so let's quickly apply this to one more example where we conserve some energy. So we're going to look at chapter 5, example number 9. This is great. So a 0.25 kilogram block travels on a frictionless surface at 10 meters per second. It hits a spring mounted on the wall and compresses it by 40 centimeters. What is the spring costing? Okay, so let's draw a picture for this. And I think what we need is a before and after. All right, this is a common kind of picture for conservation of energy questions, right? So we're going from kinetic energy, right, it's traveling at 10 meters per second, to spring potential. It's compressing it. So let's draw that picture. So our before picture looks like this. I've got a block traveling with some v initial. I could even label it as 10 meters per second. I know the mass of this block is 0.25 kilograms. And it's going to hit a spring. That's not where I want those to be. And put a little stopper on the spring. So the spring is not compressed at this point. So the spring is not storing any energy just yet. And my after picture has the spring compressed, and the block has just come to rest. So if you imagine this system dynamically, what's going to happen? Well, the block hits the spring, it slows down, until all of the energy is converted to spring potential, and then the spring gives that energy back and it shoots it backwards at the same initial speed, right? So it would come in at 10 meters per second to the right. It would leave at 10 meters per second to the left if we're assuming there's no friction and no losses to other kinds of energy. So V final here is 0. And my delta x, right, my compression here is 40 centimeters. And again, what we're looking for is the spring constant. Okay, so we're going to use conservation of mechanical energy here. And again, the reason we can use conservation of mechanical energy is because we're excluding friction. So we'll say E initial equals E final. Specifically, that's K initial plus U initial. And we should include all of the potentials we can think about. So we can say UG initial plus US initial equals K final plus UG initial plus US, sorry, not initial, final. UG final, US final. Okay. A couple of these we can count off immediately. Right? Initially, the spring is not compressed, so initially delta x is 0. So I expect there to be no stored energy in that spring. Right? Finally, the speed is 0. So there's no kinetic energy at this point that I've called final. And let's think about gravity. Do I need to think about gravity here? Well, no matter what I call y equals 0, UG is not changing. So I could subtract it from both sides, and that doesn't ruin anything. The other thing I could do is call the ground y equals 0, and then this one is 0, and this one's also 0. Okay, so it's good to think about gravity, but in this case it doesn't make any difference because we're not moving up or down. Okay, so I've got K initial equals U final, US final. That makes this nice and simple, right? So half m v initial squared equals half k delta x final squared. Okay, so at this point I'm just plugging in. I can multiply both sides by 2 to make that half go away. The mass, again, was 0.25 kilograms, so 0.25 kilograms times v initial is 10 meters per second, I think, squared, equals k times, I can do better, there, times that 40 centimeters, and let's do this in SI, so that's 0.4 meters squared. And so you can do this math, and you can get to an answer. And what I get is 160 newtons per meter. Okay. So now we have a sense that we could use this in other kinds of systems, right? You could have a system that does include gravity, and that makes the math just a step more complicated, but it's essentially the same thing. We're just accounting for all of the energy conversions in the system, and we'll see more examples of that in the future.